Welcome to SanfordFlipMath, the home edition. We are continuing to work from the Larson Battaglia version of AP Calculus. We are in section 4.1B, which does correspond to the Finney, Demanowitz-Kennedy book 4.253, kind of, sort of. We are continuing with the idea of integration, also known as antiderivatives, specifically indefinite integrals, which basically just means do the antiderivative. We started this on the last video, and we are continuing on with really just a few more examples. So a little more practice, a few more examples. Again, these problems come straight from the book, the Larson Battaglia book. So here we are, hence the abbreviation L4.1B. So that's where we are in the curriculum. Okay, so we're going to do antiderivative, which shockingly means undo the derivative, which we talked about before. Just a reminder that we have a big old formula sheet kind of thing on, I believe it was page 282. Here it is in all of its glory. Derivatives down the left side, antiderivatives down the right side, and they are set up correspondingly. So like when you see the derivative of secant is secant tangent, well, the antiderivative of secant tangent is secant plus c. Don't forget the plus c, because there could have been a constant there. All right, so all that to say is we're just going to work on some more examples, okay? All right, so as I look at this, I don't have a quotient rule for undoing derivative, so I'm going to rewrite this, and I'm going to do a couple of things here, and let me talk about what I did. There is that property, and I do believe it's on our sheet. I mentioned it in the last video, but I don't think I ever pointed it out, where if you have a constant inside the, here it is right here. If you have a constant inside the derivative, can't do this with a variable, but if you have a constant, you can pull it out in front, which lets you just focus on this and not worry so much about that. It just kind of comes along for the ride. So there it is. Okay, and all the stuff that we're doing here is in here, right? Derivative of a constant 0, the antiderivative of 0 would be a constant. Isn't that clever? Derivative of kx, a number times x, is k, so the antiderivative of a number is back to that kx, and plus c. All right, so enough of that. You can browse that at your leisure, make connections with the derivatives you know, because you're just undoing them. Okay, all right, so here I am. I'm pulling that constant out in front. This was 1 over x. You know, you could have thought of this as that. So I pulled the negative 3 out front, and x to the 7th in the bottom is the same thing as x to the negative 7th. So I am just following that rule that says if I'm undoing derivatives, so I'm going to add 1 to the exponent and divide by the new exponent. So I'm going to add 1. So I'm going to bring the -3 along. I'm going to add 1 to that exponent, so it becomes x to the -6. I'm going to divide by the new exponent. Don't forget that there could have been a constant there. And this is done. Of course, I'm going to clean that up a little bit. -3, -6, so that's a 2 in the bottom. That's an x to the 6th in the bottom. So I'm going to write that like that. Okay. Again, not necessary to simplify on a free response question, but when you're looking at multiple choice questions, when you're checking answers, etc., you need to at least be able to recognize that this is right. All right, number 24. Don't freak out with different variables. So it's theta, who cares? It's with respect to theta, so that all makes sense. So if this said theta and this said dx, then we'd be in a whole different spot. Okay, that'd be a whole different thing. And then, you know, I don't know what's going on because it's been a long time since I've done that. All right, so we have a property that says that if you're doing the integral or the antiderivative of things added or subtracted, you can literally go through piece by piece and do those separate pieces. Not true for products, not true for division for quotients, but for addition and subtraction you can. So I'm going to think of this as the integral of theta squared d theta. I'm not going to write that though. That's funny, I said I'm not going to write that even though I just literally wrote that. Okay, so generally I am not going to write this, but if you wanted to do that, you can. It's still how I'm going to think about it though. This is just a power. It's a power function. It's just like x squared. So I'm going to add 1 to the x. I'm undoing derivative. So I'm going to add 1 to the exponent, divide by the new exponent. Plus, now I need you to shift your thinking. What did we take the derivative of to get secant squared? So as promised, those derivative rules are going to be here for your whole life of calculus. Okay, so you either look at the list, or what you should have it in your knower, the derivative of tangent is secant squared. So this is going to be tangent. And then remember, when we're done, we're not done. We have to do plus c. Hey, that was it. That was fun. I don't even have to clean that up. That is awesome sauce. All right, solve the differential equation. Now remember, a differential equation is an equation with differentials in it, derivatives in it. So notice I have a second derivative here. Okay, we did one similar to this at the end of the last video, if you were still with me. So we need to undo derivative. Now, technically, if I was going to be all careful about notation, I'd be saying d2y over dx squared equals x squared. So I'm going to do I'm going to separate variables. And then we'll do the antiderivative. And I know that notation is funky. Sorry, that's supposed to be like a long S shape. There it is. Okay, so this just becomes dy. Okay, so we undid one derivative. And there will be a constant, but we'll do it on the right. Okay, antiderivative of this is now going to be x cubed over 3, add 1 to the exponent, divide by the new exponent, dx plus c. Now, most people are not going to write that. They're just going to leave it f prime, after we undo derivative, is going to be the antiderivative of x squared dx. Now, this is still f prime, hence this is just dx, because we're undoing it once. Okay, so this becomes x cubed over 3 plus c. And again, this is f prime. Now, to get this c, I'm going to use this. Now, this says f prime, and this is f prime, so f prime of 0 is 8. So 8 equals, I'm going to plug in 0. Well, that's cool. That's gone. Love that. Beautiful. We have some more of that. I love 0. Okay, so f prime equals x cubed over 3 plus 8. Okay, so that we're not done though, because that still has a derivative in it. So if it says solve the differential equation, oh, I'm off screen, I'm so sorry. You were probably yelling at me, but I couldn't hear you. All right, so again, I substituted 0 and I substituted the 8. I solved for c, there's the 8, and then we rewrote it with the 8 in there. All right, one more to go. F is going to be the antiderivative or integral of f prime. So this is, just going to write that down. And I need the dx, that's part of that notation. Okay, so antiderivative of x cubed over 3 is going to be x to the 4th over 3 over 4 divided by 4. This really ends up being 12. If it makes you feel better, you can pull the 1/3 out in front. Then you have x to the 4th over 4 times the 1/3. There it is. Just understand that that 1/3 would only be in front of this piece, not this. So if you were going to write it like that, you'd have to split that up. Plus, the antiderivative of 8 is 8x. And then I need a plus c. Now again, this is f of x. I'm going to put in 0.4 to find out what c is. So I'm going to put 4 in place of f of x, in other words, y. I'm going to put 0 in. Okay, and I know most of you are just going to go, come on, that stuff's 0. Why are you writing all that? I gotcha. So all that's gone. C is 4. So I'm going to rewrite now. F of x equals x to the 4th over 12 plus 8x plus c, which is 4. Okay, so there is my final answer, and I know stuff's starting to run together because I'm trying to be economical with paper, but etc. I know I don't want to confuse you. Okay, so just so we're clear, I started going like this, and I was worried the notation was getting too cumbersome. So I kind of started over again here, and then I went to here, and then up here, down through there. Okay. All right, so I'm going to move. So if you need to, or if you're still writing, hit pause. Okay. We're going to do 2 more problems. Hopefully this won't be as long as the last one. I know the last one was long. Sorry. Number 50 is kind of a weird question. Number 50 is one of those do some stuff and look at it questions. So it says, Again, this is from the Larson book. Consider f of x equals tangent squared x. Okay, that's this. And g of x equals secant squared x. Okay, what do you notice about the derivatives of f and g? And then what can you conclude about the relationship between f and g? Okay. All right, so we're supposed to do the derivatives of each and then stare at them. Okay, so I'm going to do f prime. Okay, so again, this is derivative now. We're not doing antiderivative, we're doing derivative. Now, worth noting that tangent squared is really the tangent squared. So I'm going to have to do some chain rule stuff here. Okay, so 2 times, keep the inside the same, to the first power, times the derivative of the inside. Okay, there's really not much to clean up here. I'm going to go ahead and write 2 tangent x secant squared x just to, I don't know, to get rid of the unnecessary stuff. Okay, I'm going to do g prime. Now, same idea. This is really secant x squared. So I'm going to do power rule, 2 times to the first power. Okay, and the inside stays the same. And the derivative time, and then I need to multiply by the derivative of the inside. Well, the derivative of secant is secant tangent. So I'm going to clean that up. So I have a 2 times secant times tangent. All right, so what we're supposed to do then is stare at those. Okay, so look at this here and look at this here. And what do you see? Suddenly I'm feeling like Dora. What do you see? Yeah, I see that too. Well, so here's my question to you. If you did the antiderivative of 2 tangent x secant squared x, what do you think the answer is? So if I do the antiderivative of this, because they're the same, what's the answer? Well, it looks like it could be tangent squared x. Let's see. It also looks like it could be secant squared x. Let's see. Isn't that crazy? That's amazing to me. 2 functions that obviously they're related because they're trig functions, but they are significantly different. But they both give the same derivative. So if you turn it around and do the antiderivative, we got options. And because of what we use the antiderivative for, that's really not freaking me out, because really this ends up getting used for a purpose, for finding volumes, for finding not just volumes, but also areas and things like that. So that's not a shock to me. Okay. All right, so let's do one more problem and then we're going to be done. A balloon is rising. Okay, so I think they're thinking like a big balloon, one of those balloons where you see people like flying around and stuff. It's going up. Okay, it's going up. And when it gets to 64 feet up, they drop a sandbag out. Okay, I will say that the rest of this problem is all about this sandbag. It has nothing to do with the balloon. This whole problem could have been done with a 64 feet building, and we have a dude up here, didn't have to be a dude, and he throws something off the building, and then it starts falling. Okay, so we have a balloon rising. They drop a sandbag when they get 64 feet up. Okay, and then the question becomes, when does it hit the ground, and how fast is it going when it hits? Okay, all right, so there are some things that we need to put together. First of all, we are told the acceleration due to gravity is negative 32 feet per second squared. And I need you to remember that if I have a position, in this case a height, then h prime is how fast it's going, and h double prime is its acceleration, right? So we talked about this before, when we're talking about derivatives in the derivative chapter, the relationship between position, in this case height, how fast it's going, its velocity, and its acceleration. So all that means is h double prime of t is negative 32. Well, from this, we're supposed to get, when does it hit the ground? Well, isn't hitting the ground about a height? And once we get the when, once we get the time for that, and worth noting that the book words it nicer. It says, how many seconds after its release will the bag strike the ground? And I just, being the essence of lazy, wrote when will it hit the ground, okay? So if I need to know h equals 0, I need to know the t equals for h equals 0. So look at me identifying the symbols that I know and the symbols that I want to know, right? This is how I do math, right? And now I need to make those symbols happen, and all I get is this to start with. Well, what that means is I need to work backwards. I need to work back from second derivative. That's not a notation, that's just me drawing your attention to it. I need to undo derivative. So I'm going to say h prime, also known as v, equals the antiderivative of negative 32 dt. Now it's about t, so that's why it's dt instead of dx. So this is just negative 32t plus c. Now, you are going to have to infer from context what's going on. Okay, so here's my question to you. Oh, wow, I don't think we wrote that down, did we? The balloon is going up. Oh, that's a good note. I'm just noticing this. A balloon, this was 57, right? Yeah, a balloon rising vertically at a velocity of 16 feet per second. It was rising at 16 feet per second. Oh, it was there. Okay, there it was. All right. So I guess my question to you is, when we released this bag at the beginning, when time was 0, how fast was the bag going? The bag was moving at 16 feet per second. So if I'm going up in the balloon and I let go of the bag, its initial velocity was going with the balloon 16 feet per second. Is there an expectation that you'd be able to put that together? Yeah, there is. I'm sorry. All right, so the initial velocity, the velocity at 0 is 16. So I'm going to say 16 equals negative 32 times 0 plus c. Okay, so that's gone. I love it when I have 0 involved. Okay, so v equals, also known as h prime, equals negative 32 t plus 16. Okay, so that's important. Okay, one more step to go. I need to be able to put together h, this is not h, and what time is the h0. So I need an equation that's about h and time. This is still h prime. So h will be equal to the antiderivative. So the antiderivative of this, again, I can pull the negative 32 out in front of just this term, but I'm just going to go ahead and write negative 32, add 1 to the exponent, divide by the new exponent, plus 16. Well, this is 16t to the 0, add 1 to the, so this becomes t to the 1 over 1. I'm not going to write all that, plus a new constant. Now, if these separate constants are bugging you, that they're different, then you can call this C1 if you want. You can call this C2. Nobody gets excited about that. Okay, just as long as you understand that these numbers are not the same C's. Okay, so this is now h. Well, what was the initial height? We know what the height was at time 0 because they said they let go of this 64 feet up. So when they let go of this, it was 64. Okay, so here we go. I'm going to plug in 64 equals negative 32 times 0 squared plus 16 times 0 plus C, C2 if you like. Okay, so I guess C is 64 for that, and I am running out of room on this little sheet of paper, so I will start a new one. How about that? H of t equals negative 32 t squared plus 16 t plus 64. Whoop, running out of space there. All right, there we go. So this is my final equation. Okay, so the question says, when will the bag hit the ground? So I need to do negative 32 t squared plus 16 t plus 64. The height there is 0. I need to solve this. So I see a common factor of 16. I'm going to divide both sides by 16 because I'm way lazy. Okay, and so this becomes negative 2t squared. Oh, I should divide by negative 16. Sorry. Positive 2t squared minus t minus 4. This is going to be ucky. 0. That's not cool. Did I mess something up? I hope not. 16 into 64. That's right. I'm just looking at this thinking this is probably not going to factor. That's all. Okay, so t equals 1 plus or minus the square root of b squared minus 4 times 2 times negative 4. I'm really careful with the 4ac over 2. So this is now 8 times 4 is 32 plus 1 is 33. Be really careful with signs. Over 4. Okay, so obviously 1 minus the square root of 33. 1 minus the square root of 33 is going to be negative. So that's not going to be useful. All I need is the 1 plus the square root of 33 over 4. You may want to do a decimal for that. Okay, I'm running out of time, so I don't want to keep going too hard with this. The second question was, what was the velocity when the bag hits? So this is a t value. Velocity is from the derivative. So take that number and plug that in, and that's the other question. Okay, not cute, but that's what it is. All right, thanks so much for being here. It was lovely having you. This is SanfordFlipMath, the home edition, and we're out of here. Bye.